Obviously, there is a cost involved at entering and exiting from the scope, meaning to say that when you enter a scope, you have to push a variable onto the stack. When you exit the scope, you have to pop it off the stack. But you are doing that anyway, as far as the runtime stack is concerned, so that's not a big cost. The cost begins when you meet a variable that you've never met before. So now you have to create a stack, or when you pop off the stack, the last variable that's still there. So now you have to destroy the stack. So there's an edge cost when you actually creating stacks and destroying stacks. When you're pushing under the stack and popping off the stack, you would have done that anyway on the runtime stack. So instead of doing it on the runtime stack, you're actually doing it over here. There are actually costs besides what I mentioned involved in this structure. First of all, notice that I have the variables not in the runtime stack, but somewhere else. You might say, who cares? What is the difference if it's in the runtime stack or it's not in the runtime stack? True, but in a sense, as I said, it's more complicated to move in and out of scopes. That's issue number one. Issue number two is types. What does that mean? Well, who guarantees that mains A, could be of type don't care, and X's A could be of type I really don't care. Notice that's a different type. It's not the same type. So how can I create a stack in a sense that that holds different types of types? Now I have to be able to access those types, have to be able to pop them in, pop them out. So yes, I can create some global objects and pop in objects and pop out objects, but notice that there's an inherent problem here that the types are not necessarily congruent. And therefore, you can't push on the same stack, right, different types of types and have everything run smoothly. So this is obviously a problem. The solution to this problem is that shallow access does not put the variables on all these stacks that I mentioned. The variables remain on the runtime stack. That's where they remain. What's in all these side stacks or variable stacks, whatever you want to call them, is just a pointer to the correct location in the runtime stack. Meaning to say that when we placed main on the runtime stack and we had a variable A and a variable B, if I'm not mistaken, right? A variable A and a variable B, the variables are actually on the runtime stack. But all we did is we said, okay, here you have a pointer. You have a pointer to the location on the runtime stack. So this will point to right there, and this will point to right there. Okay. Now, when X goes on the stack or Y went on the stack, so Y had a B in it. So Y, it's not that the Y's B is going to be on this variable stack, but B will have a pointer to the runtime stack where B is actually at. Same is true for all of X's A's. You will have 25 pointers into the runtime stack. Same is true for X's D's. And same is true for all variables. Now, why is that? Why does that make a difference? It makes a difference because now all of the things pushed on the stack are of the same size. They are all pointers. They can be handled in the same way. Now, notice that I'm not wasting a lot of memory because that would be a question of what is the ratio of pointers to the actual data types involved. If you are storing on the runtime stack just integers, so then you're actually doubling your memory. But if you are you're storing the big structures and you're just adding another pointer, then the ratio is actually pretty small, and therefore the cost is not that high. You will have to actually, as I said, still deal with it when you move into a scope and move out of scope. So when you move out of scope, you have to pop. Besides cleaning the runtime stack, you need to pop the pointers off the variable stacks, which we have to do. But in the shallow access solution that we're describing right now, then you don't have to know the names of the variables in the runtime stack, even for the dynamic scoping, because who cares what they are? The point actually is that you just access them whichever way you want to access them by using the pointers. There is one more cost that has to be discussed when we talk about a shallow access, is the cost of accessing the variables. Notice that every access is a double access, meaning even if I go and implement it using pointers, what actually happens is that when I say C out A plus B and I say A, so I go to the run, I go to this A stack and I look at the top pointer of the A stack. That is the dynamic scoped variable that I need to talk about. And then I use that pointer to access the variable on the runtime stack. So I'm actually using a double access and everything becomes more complicated and takes more time. But that doesn't mean that it's bad, because when we talked about, for example, static scoping, so you also every a variable access which was out of scope means like further up the scope tree. So I had multiple accesses using all these pointers. So that's not bad. So right now we're actually getting everything in a constant step, which is an improvement over what we had before, which we had things in not the constant steps. The problems with dynamic scoping are not, as I said, implementation issues, because we were able to overcome those with shallow access. There is a cost involved, as I said, with running all these named stacks. But I think that's not the real reason why it's actually not used in a lot of languages. I think it's not used in a lot of languages because it's not very intuitive, which means when you have a line of code, it's very hard to look at the code and reason about it. Meaning when a programmer has to go and decide, should he change the code, shouldn't he change the code, should he do it, shouldn't he do it, it's very, very difficult to reason about dynamic scoping. Again, taking a look at this piece of code, what is actually meant. Now, this is a simple piece of code. We give it two interpretations. And it will be a function of who called who and when. So it's actually very difficult to reason about this type of code. And that's probably the main reason why it hasn't been accepted as a standard in industry. And we actually most languages use static scoping because it's a lot more easy to reason about, to write proofs about. There's all kind of proofs about code. You want to prove all kind of traits about the code, show that it's actually adhering to some kind of rule, all kind of things like that. And when you use dynamic scoping, that's almost impossible to do. And in static scoping, it is possible. So although supposedly we showed that static scoping is actually more difficult and had to, in a sense, maybe implement, and also has its deficiencies, but dynamic scoping has the major deficiency that it's very, very hard to reason about code.